Space isn't what you think it is. We're told it stretches outward in all directions, an endless horizon of stars, planets, and galaxies. But that's only part of the truth. What if the biggest secrets aren't out there in front of us, but above and below us? Because while we've been focused on orbit paths and planetary alignments, something else has been happening, right over our heads and far beneath our familiar plane. Strange structures, invisible forces, and high-speed radiation are quietly shaping everything we know. Magnetic tunnels, ghostly bubbles, rogue planets, even dark matter highways. They're not myths, they're real, and they're hiding in the vertical layers of space we rarely talk about. And once you realize what's up there and what's coming from below, you'll never look at the night sky the same way again. This isn't just astronomy, it's a new map of reality, one we've been ignoring until now. Well, when we picture the solar system, we usually imagine a flat stage, planets orbiting neatly around the sun, each locked into its path like marbles rolling on an invisible disk. And that's not entirely wrong. Most of the mass and motion in our solar system actually reside along this thin plane called the ecliptic. It's the way our system formed, from a spinning cloud of gas that flattened out over time, shaping the orbits of planets, moons, and asteroids. But that's just one angle. What we rarely talk about is what exists above and below that flat plane. Because space isn't two-dimensional, and the solar system doesn't float in isolation. It's sitting inside a much larger, layered, and surprisingly structured galaxy. And when you start looking at it vertically, peering straight up past the poles of the sun, or plunging downward beneath the planetary dance, everything changes. There are powerful solar winds blasting from the poles, invisible fields stretching into interstellar space, clouds of plasma and rogue interstellar dust drifting down from the dark. There are gamma-ray structures above us the size of galaxies, and high-energy cosmic rays that rain down from above, slamming into Earth's atmosphere with origins we still don't fully understand. So the real question is this: what's out there in the vertical? Because once you tilt your view, the solar system stops being a tidy clockwork model and becomes part of a dynamic, three-dimensional storm of forces, fields, and cosmic mysteries we're only beginning to uncover. We've mapped planets, we've studied moons, we've even flung probes into deep space, but our mental picture of the universe is flat. Most people never think in three dimensions when it comes to space. They don't ask, where does the solar system sit inside the galaxy? What's rising above it, stretching beyond it, falling beneath it? And what invisible forces could be pulling us, without us even noticing? To really understand the universe, we need to flip the map, because the most important things aren't always in front of us. Sometimes they're right above our heads. The galactic North Pole. You've probably heard the phrase, "There's no up in space." And technically, it's true. When you float outside Earth's atmosphere, there's no floor, no ceiling, no gravity to pin you to a direction. You could spin in any axis and never know which way is up or down. But despite that, space isn't directionless, because if you want to navigate the galaxy, launch a probe beyond Pluto, or simply ask the question, where exactly are we? You need a fixed point, something stable, something that doesn't change when planets wobble or stars move. That's where the galactic North Pole comes in. Now, this isn't the same as Earth's North Pole. Earth's poles are based on the planet's rotation, where it spins like a top, with the Arctic and Antarctic at either end. That's useful here on Earth, but not much help when you're out in deep space, trying to figure out your place in a swirling galaxy filled with billions of stars. The galactic North Pole is something far bigger. To understand it, imagine this. Picture the Milky Way as a giant cosmic frisbee, thin, flat, and spinning through space. Our solar system is embedded somewhere on one of the outer arms, like a speck of dust near the edge. If you drew a line straight up, at a perfect 90-degree angle from the surface of that spinning disk, you'd be pointing toward the galactic North Pole. It's not a place you can visit. It's not a planet, a star, or a cloud of gas. It's a direction, a line through space, but that line, oddly enough, gives us a kind of up in a universe that doesn't officially have one. And it's absolutely vital. Astronomers use it like a galactic compass needle. If you're charting the motion of the solar system, measuring the tilt of the galaxy, or building a coordinate system to describe where objects are in 3D space, you need that pole. It becomes your anchor, your frame of reference, the one thing that doesn't drift. So even though the galactic North Pole doesn't shine like Polaris, the North Star we use on Earth, it might be even more important, because without it, you're just floating blind in a sea of stars. Now here's where things get interesting. This galactic up doesn't sit over Earth's North Pole. Earth is tilted, about 23.5 degrees from the plane of its orbit. The Sun is tilted too, in a different direction compared to the rest of the galaxy. So when you trace that line, pointing to the galactic North Pole, you end up aiming at a quiet patch of sky in the constellation Coma Berenices. It's not a famous constellation. There are no bright stars lighting it up, but that's actually what makes it so useful. You see, the galactic plane, the equator of the Milky Way, is incredibly messy. It's jam-packed with stars, dust, gas, nebulae, and all kinds of bright distractions. Trying to look through it is like trying to peer through a smoke-filled city. You can't see very far before the light gets scattered or absorbed, but if you look straight up toward the galactic North Pole, you're looking through one of the clearest, cleanest windows in the sky. There's almost no dust in that direction, hardly any foreground stars. It's like peeking through a cosmic skylight. That's why some of the most important space missions, like the WMAP, Planck, and Chandra X-ray Observatory, have aimed their detectors there. Because when you want to study something faint and far away, like the cosmic microwave background or ancient quasars, you want the sky to be as clean as possible, and the region around the galactic North Pole is one of the best spots we've got. Think about it this way. If the Milky Way is a bright, glowing disk, then looking through its center is like trying to spot a flashlight through fog. But when you look out the top, through the pole, you're staring into deep time. You can see galaxies that formed just a few 100 million years after the Big Bang. You can study background radiation that's been traveling toward us for over 13 billion years. You're not just looking at space, you're looking at history. But the galactic North Pole isn't just about getting a better view. It actually helps us understand how the galaxy is built. Even though the Milky Way might look flat from afar, it's not a perfect disk. It's warped, it's rippled, it's lopsided. To figure that out, you need a fixed coordinate system. That's why astronomers use galactic coordinates, a system kind of like latitude and longitude on Earth. Instead of measuring from Earth's equator, though, it measures from the Milky Way's plane. In this system, the center of the galaxy is at 0 degrees, 0 degrees, and the galactic North Pole is at 0 degrees plus 90 degrees. Simple, elegant, and extremely powerful. This lets scientists describe the position of any star, cloud, or planet with just two numbers, galactic longitude and latitude. It's how we chart stellar motion, map the spiral arms, and even track mysterious forces like the Great Attractor, a hidden mass that seems to be pulling entire galaxy clusters in one direction. None of that would make sense without a clear up. Without the galactic North Pole, we'd be describing everything with messy, wobbly references that change over time. This gives us consistency, and it matters now more than ever, because Earth isn't standing still. Neither is the Sun. The entire solar system is rotating around the center of the Milky Way, once every 230 million years. But we're not just circling, we're bobbing. Like a boat on a wave, the Sun gently moves above and below the galactic plane every few tens of millions of years. Right now, we're ever so slightly above it. And here's the twist. Some scientists think this vertical motion through the plane, through the up and down of the galaxy, might influence things on Earth. There are studies suggesting that mass extinctions, comet showers, or even shifts in Earth's climate, could be linked to our passage through dense regions of the Milky Way. When we dip below or rise above, we may encounter more interstellar dust or disrupt the Oort cloud, flinging comets inward. We don't know for sure, but it adds a strange kind of weight to the idea of galactic up. Because maybe, just maybe, what lies in that direction affects life on Earth in ways we haven't fully grasped. And speaking of what lies above, when we point powerful telescopes toward the galactic North Pole, we don't just see open sky. We see structure. We see the galactic halo, a ghostly sphere of dark matter and ancient stars that wraps around the galaxy. We see the Fermi bubbles, giant lobes of gamma-ray radiation that rise above and below the galactic center. We see the strange arc of the North Galactic Spur, a winding filament of gas and dust that curves upward like a bridge to nowhere. And beyond all that, we peer into the Laniakea supercluster, the enormous cosmic basin that the Milky Way drifts through like a leaf in a vast ocean of galaxies. All of it begins with a line, a direction, a point in the sky that doesn't shine, but still tells us which way is up. The galactic North Pole is more than just a coordinate. It's our orientation. It's the scaffolding for our maps, the lens through which we study the ancient universe, and a reminder that even in a world with no absolute directions, we still need something to aim for. So next time you hear someone say, "There's no up in space," you'll know that's only half true, because while up may not exist the way we're used to, when you look toward the galactic North Pole, you're staring into the purest version of it we've got. And behind that dark, empty-looking patch of sky is everything we haven't discovered yet. A strange magnetic gateway. Go straight up from the sun's North Pole, past the flicker of light, beyond the pull of planets, and you'll enter one of the strangest, least understood zones in our cosmic neighborhood. Now don't imagine this as just up, like climbing a ladder. In space, direction is all about reference, but if you stood on the surface of the sun, assuming you could survive, and launched yourself straight out from the North Pole, you'd leave behind something more than heat and light. You'd rise through a region where invisible forces dominate, where magnetism replaces gravity, where the air isn't air and wind isn't wind. This is a space shaped by energy, carved by particles and sculpted by plasma you can't see, but would absolutely feel if it weren't for the protection of Earth's magnetic field. This is the solar polar region, and above it lies a vertical pipeline into interstellar space. Right near the sun's poles, the environment behaves completely differently from its more familiar equator. While the equator crackles with sunspots and bursts of solar flares, the poles are much quieter. But quiet doesn't mean inactive. It's a deceptive silence. Instead of eruptions, the poles produce speed. Not violent explosions, but steady, persistent outflows. This is where the sun exhales. The solar wind, something you've probably heard about in science class, isn't actually one wind. It has layers, textures, speeds, and the wind that escapes from the sun's poles is some of the fastest, cleanest, and most direct in the entire solar system. It jets out into space in narrow beams, not unlike water blasting from a fire hose. But these aren't gusts of air. They're streams of ionized particles, mostly electrons and protons, that are ejected at speeds of over 700 kilometers per second. That's nearly 2.5 million kilometers per hour. These particles are born in the sun's corona, the superheated outer layer that can reach temperatures of over 1,000,000 degrees Celsius, and are carried into space by magnetic field lines that near the poles are open-ended. They don't loop back to the sun. They stretch outward into the dark, allowing particles to slip through and sail into the vastness. Back in the 1990s, a European-American mission named Ulysses took a risk. It wasn't like other spacecraft that orbit around the sun's middle. Ulysses was designed to do something different, fly over the sun's poles. It was a bold move because it meant taking a strange path, slingshotting around Jupiter to bend its orbit and push it out of the usual flat solar system plane. For the first time, we got a look at what lies above the sun, not from theory, but from actual data, and what Ulysses found changed our entire understanding. It detected that the solar wind above the poles was faster, less dense, and far more uniform than the chaotic streams coming off the equator. At the equator, the sun's wind is messy. It's tangled in magnetic loops, twisted by sunspots, and interrupted by bursts of plasma. But above the poles, it's like entering a current, straight, clean, consistent. This wind doesn't pulse, it flows. But why is that important? Because that flow shapes the entire solar system. It's what defines the heliosphere, the massive bubble around our solar system, created by the force of the sun's outflowing wind. Think of the heliosphere as our star's personal shield. It pushes against the interstellar medium, keeping out a large portion of harmful galactic radiation. And the solar wind from the poles. It's what helps maintain that bubble's size and strength. It's like pressure from the inside of a balloon, keeping it inflated. The region above the sun's north pole is the sun's cosmic chimney. Through this, the sun vents its energy, creating a vertical corridor that pierces the galaxy. It may look empty, but it's a high-speed highway of particles racing away from the sun, sometimes interacting with each other, sometimes curling along magnetic field lines that extend for billions of kilometers. The structure here is fascinating. Magnetic field lines twist and curl in the sun's atmosphere, but at the poles, they stretch. Picture the spaghetti-like loops snapping and opening like a drawstring bag. The magnetic field becomes radial, pointing straight outward, allowing plasma to travel freely, unhindered by the tight magnetic bottle that holds it in elsewhere. This openness means the solar wind in this direction is not just fast, it's also clean. Free from the dense tangle of solar activity, it becomes a stable stream that allows scientists to measure its properties with much more precision. That's why spacecraft studying space weather often rely on polar measurements for long-term predictions. But keep climbing, and things start to change again. Eventually, you reach the outer limits of the heliosphere, the edge of the sun's influence. This boundary is known as the heliopause, and it's a big deal. It's not a sharp wall, but rather a transition zone where the solar wind slows down and gets pushed back by the interstellar medium, the gas and dust that fills the space between stars. Voyager 1, launched in 1977, crossed this boundary in 2012. And where did it exit the solar system? Near the sun's northern flank. That means it passed right through the very region we're talking about, above the sun, into the cold unknown. Once you're past the heliopause, the sun's protection fades, the temperature drops, the magnetic field shifts, and the influence of the galaxy begins. It's like walking out of a city's light pollution and seeing the raw stars for the first time. Cosmic rays, those high-energy particles from supernova explosions and other deep space phenomena, begin to pour in. And because the polar heliosphere is less turbulent, it also acts as a gateway for these galactic intruders. During solar minimum, when the sun's activity is at its lowest, this gateway widens. The solar wind weakens, the magnetic field becomes less structured, and cosmic rays find it easier to sneak in. These rays don't just stay in deep space, they make it all the way to Earth, influencing satellite electronics, astronaut safety, and even, according to some studies, cloud formation and climate. This makes the region above the sun not just fascinating, but relevant. It's not some far-off curiosity. It's a living boundary that decides what gets in and out of our solar neighborhood. Even more fascinating? The sun's motion through the galaxy also plays a role in shaping this zone. The sun doesn't sit still. It moves through the Milky Way at breakneck speeds, over 800,000 kilometers per hour, and that motion creates a kind of interstellar headwind. Guess which direction it comes from? Mostly from above. The sun's apex, the direction it's traveling, is slightly tilted above the galactic plane, meaning the region above its north pole is also where it's plowing through interstellar space. So the solar wind, the heliopause, and the interstellar medium are all colliding in that direction. It's not just a stream, it's a battlefield. Charged particles and magnetic fields from the sun are slamming into the dust, gas, and fields of the galaxy. That clash creates shock waves, compressions, turbulence, and possibly new, still undiscovered physics. Future missions like NASA's Interstellar Probe are being designed to head straight into this zone, to map what's really going on above the sun and beyond the heliosphere. They want to measure the shape of the boundary, track how it shifts over time, and maybe even catch sight of what lies on the other side. Because here's the twist. Some scientists believe the heliosphere isn't a neat, round bubble. It might be warped, squished, or shaped like a deflated balloon. And that distortion, it could be strongest in the polar direction. In other words, above the sun may not just be a smooth exit, it could be the weak spot, the place where things get in, the place where the sun's influence finally fails. And if that's true, then we're looking at more than just a strange magnetic gateway. We're staring at a leak in our solar system's force field. We used to think of space as quiet, empty, still. But the more we look above the sun, the more we realize that it's anything but. It's windy, it's electric, it's alive. And whatever lies beyond it, whatever's waiting in the interstellar dark, it's already knocking on the door. The solar apex. Here's something most people never think about. We're moving. Not spinning on Earth, not just orbiting the sun, but the entire solar system is flying through space. And it's not just moving slowly. It's tearing across the galaxy at an incredible speed, about 828,000 kilometers per hour. That's fast enough to circle the Earth more than 20 times in a single hour. But what's really wild is where we're going, because this journey has a name. Astronomers call it the solar apex. Now let's be clear, this isn't some random path. We're not drifting aimlessly like space dust caught in a breeze. The sun is locked into the Milky Way's structure, pulled by gravity, steered by mass, guided by invisible cosmic rivers. And the solar apex is the name for the direction the sun is headed, right now, in this moment, through the galaxy. It points roughly toward a bright star called Vega, located in the Lyra constellation, which itself lies in the general direction of Hercules. But don't get caught up in names. The important part is this: our solar system is climbing, literally. We're not just moving around the galaxy in a flat loop. We're tilting upward, like a car accelerating up a hill. And this tiny vertical angle matters more than you might think. Because as we move forward, we're also rising above the galactic plane, that dense midsection of the Milky Way, where most of the stars, gas, and dust live. So the solar apex isn't just a horizontal heading, it's an inclined pathway, a kind of diagonal chute through space that's taking us into thinner, stranger, more mysterious territory. But where does that trail come from? Why are we even moving at all? Let's zoom out for a second. The Milky Way is huge, around 100,000 light-years across, and everything inside it is rotating. Our solar system is orbiting the galactic center, making one full circle every 230 million years. This orbit is not a perfect circle, and it's not perfectly aligned with the galaxy's disk. The sun doesn't just follow a flat track like a race car. It bobs, rising and falling above and below the galactic midline over millions of years, like a gentle wave. But alongside that wave-like motion is a forward trajectory, a gravitational flow toward a very specific part of the galaxy. That's the solar apex, and that movement reveals a lot about our cosmic environment. First off, the motion itself isn't just some background detail. It shapes how we interact with everything around us. As we move toward the apex, we're essentially flying into a cosmic headwind, and that wind isn't made of air. It's made of interstellar particles, magnetic fields, cosmic dust, and high-energy radiation. Imagine driving down a highway during a snowstorm. The snow doesn't just float, it's slamming into your windshield. That's what the solar apex is doing for the solar system. The heliosphere, the giant magnetic bubble around us that's inflated by the sun's solar wind, is being pressed on its front side. That side faces the solar apex, and it's shaped like a nose, squashed inward like a balloon hitting a wall. It's not symmetrical. The back end of the heliosphere, the tail, is stretched out far behind us. We're moving forward and upward, which gives the heliosphere a teardrop shape, and that teardrop is constantly shifting, changing, reacting to whatever we're flying into. This forward motion also affects how we experience cosmic rays, those tiny high-speed particles from exploding stars and distant galaxies. As we head toward the apex, we're basically plowing into more of them. We get hit harder. The sun tries to block them, but during solar minimums, when the sun is quiet, they sneak through. That's why spacecraft like Voyager 1 saw a huge spike in cosmic radiation as it moved near the heliosphere's edge in the direction of the solar apex. Out there, the shielding fades, and the space around us gets loud with particles we can't see, but definitely don't want to meet unprotected. Now let's talk about the neighborhood. The direction of the solar apex leads us into a region called the local interstellar cloud. It's a patch of slightly denser gas and dust, roughly 30 light-years wide, and we're currently inside it. Yes, we're sailing through a literal cloud in space. It's not like a cloud in the sky. You wouldn't see fog. But this stuff matters. The temperature, pressure, and density of this cloud shape the boundary of the heliosphere. If the cloud gets thicker, the heliosphere shrinks. If it's thinner, the heliosphere grows. This, in turn, changes how much protection we get from cosmic rays. It's like adjusting the shields on a spaceship, but we don't control the dial. Space does. And get this, we might be heading out of this cloud in a few thousand years. On our path toward the solar apex, there could be other clouds waiting, some colder, denser, more dangerous. If we hit one of those, the heliosphere could collapse inward. That might increase radiation levels across the solar system. It could even affect the climate or planetary atmospheres, depending on how extreme the conditions are. And yet, we've never seen these clouds directly. We only infer them through starlight distortions, particle measurements, and clever mapping. Here's another wild detail. Because we're flying toward the solar apex, all our readings, like the cosmic microwave background, the afterglow of the Big Bang, get skewed. This motion causes what's called a dipole anisotropy in the CMB. Basically, the universe looks slightly warmer in the direction we're heading, and slightly cooler behind us. It's like turning on your car headlights in fog. The beams look brighter up close, fainter behind. That simple temperature difference told astronomers which way we're moving in space. In other words, we don't just track stars, we track the universe's background to figure out where we're going. But even more than that, this forward motion gives us context. By comparing the sun's motion to nearby stars, we can map stellar neighborhoods. We can spot moving groups, associations of stars that drift through the galaxy together. And by measuring where they're headed, we learn how spiral arms form, how galaxies evolve, and how the Milky Way grew over billions of years. The solar apex helps us see structure, not just motion. It's like noticing that traffic is flowing toward a city center, and then realizing that the city is growing because of it. Our path also offers something deeper, a sense of direction in a universe that feels directionless. Most people imagine the cosmos as a random scattering of stars, but it's not random at all. We're caught in flows, filaments, collapses, and expansions, and the solar apex is one of our biggest clues, because if we know where we're going, we can start asking, why? Why are we moving toward Hercules? What's pulling us? Some scientists believe we're feeling the distant tug of something even bigger, like the Great Attractor, a massive concentration of galaxies hidden behind the dust of the Milky Way. Others think it's part of a grander motion through the Laniakea supercluster, a megastructure of galaxies all drifting together. The solar apex might just be a small step in a much larger path, a kind of galactic on-ramp to something beyond our current understanding. It's like realizing your car isn't just driving down a road, it's part of a highway system you've never seen. And that raises a final thought. We often talk about looking up at the stars, but the truth is, we're heading into them. We're not just observers, we're travelers. Our star, our planets, our entire solar system, they're all passengers on a cosmic ride, and the solar apex is the signpost showing us where we're headed next. We don't know exactly what lies ahead, but we know we're moving toward it, upward, forward, into the unknown, and that's something worth watching. High-energy cosmic rays. Beyond the calm surface of the night sky is a storm we can't see, because it's a clear night. You step outside, tilt your head back, and stare at the stars. Everything looks calm, peaceful, silent, but what you can't see is that above your head, space is anything but quiet. Right now, as you breathe, millions of invisible bullets are flying through the sky, smashing into Earth's atmosphere from all directions. These aren't made of metal or stone. They're not meteors or pieces of broken satellites. They're smaller, much smaller, and faster than anything you've ever seen. They're called cosmic rays, but don't let the name fool you. They're not rays in the way we think of light. Cosmic rays are charged particles, mostly protons, some helium nuclei, a few stray electrons, moving close to the speed of light. And they don't just cruise in peacefully. They slam into our planet with such insane energy that they can split atoms apart, create showers of subatomic particles, and even mess with electronics. And here's the wild part. A lot of them are coming from above us, not just up in the Earth sense, but from the galactic north, that strange, not quite a real direction in space that astronomers use as a kind of vertical marker. We don't know exactly why there's a concentration of cosmic rays coming from that part of the sky, but we've noticed something off, something directional. These particles aren't arriving evenly from every angle. There's a slight imbalance, a cosmic tilt. More of them are entering the solar system from above the sun's north pole than below or sideways. And that raises a very big question. What's up there? Let's start with where these cosmic rays come from. Some are born in the violent deaths of stars. When a star explodes in a supernova, it hurls debris into space at breakneck speeds. That blast can push particles so hard they're flung across the galaxy, accelerating for thousands of years. Others come from even weirder places, like neutron stars, pulsars, or active galactic nuclei. These are the powerhouses of the universe, extreme places, doing extreme things, spinning, twisting, snapping magnetic fields. And when those fields break, particles shoot out like cosmic shrapnel. But even these don't explain the highest energy cosmic rays, the ones that carry more energy in a single particle than you'd find in a fast-pitched baseball. Yes, you heard that right. One tiny proton, smaller than an atom, carrying as much energy as a physical object you could hold in your hand. How is that even possible? We don't really know. Some scientists think they could come from gamma-ray bursts, the most explosive events in the universe. Others believe they might originate from the jets of supermassive black holes, or the remnants of galactic collisions that happened long before Earth even existed. And there are people, respected astrophysicists, not conspiracy theorists, who think these rays might be tied to dark matter, the invisible substance that makes up most of the universe but doesn't interact with light. And where are they coming from? Well, that's tricky. Cosmic rays are charged, which means they get pushed around by magnetic fields. By the time they reach us, they've been twisted, turned, and tangled by the magnetic fields of stars, galaxies, and interstellar space. Their path is scrambled. We don't see where they started, we just know where they ended up. But despite the confusion, instruments around the world and in orbit have noticed something consistent, a directional bias. More cosmic rays are coming from the northern galactic sky than from the south. A small difference, sure, but statistically real. That suggests the space above the solar system might be denser, more active, or more magnetically aligned with high-energy cosmic sources. And here's where it gets really interesting. Back in 2012, when Voyager 1 crossed the edge of the heliosphere, the bubble of solar wind that surrounds and protects our solar system, it recorded something incredible. The number of cosmic rays jumped. It was like walking out of a quiet room and straight into a storm. Inside the heliosphere, the sun's magnetic field helps shield us. But once you're outside that bubble, there's no cover. The universe just hits you. Voyager was traveling northward, toward galactic north, when it made that discovery. And it noticed something else. The particles weren't just more intense, they were different. The mix, the energy, the angle, they all hinted at a more active, possibly structured region beyond the heliosphere's northern edge. Other spacecraft, like Ulysses, have picked up similar signs. Ulysses had a unique orbit that took it over the sun's poles. As it rose above the solar system, it encountered higher speed solar winds, thinner particle streams, and less protection from interstellar radiation. It also detected incoming particles that didn't match the usual solar patterns, suggesting they came from farther away. And then there's the Alpha Magnetic Spectrometer, a particle physics experiment mounted on the International Space Station. It's been scanning cosmic rays since 2011, and one of the strangest things it's found is a slight excess of positrons, the antimatter version of electrons, coming from the galactic north. What's causing them? No one knows for sure. One theory: they're the signature of dark matter annihilation, tiny pockets of antimatter and matter colliding and erasing each other, releasing a burst of energy. If that's true, we're staring into a dark matter hot zone right above our heads. Now let's bring this back to Earth. Even though we're protected by the Earth's magnetic field and the heliosphere, cosmic rays still make it through, especially during solar minimums, when the sun is quieter and the protective bubble weakens. That's when cosmic rays can sneak in more easily. And where do they land? Mostly near the poles. Why? Because the Earth's magnetic field guides them there. Charged particles follow magnetic lines, and those lines dip into the Earth at the north and south poles. That's why we see auroras in those regions. Those dancing lights are actually charged particles hitting our atmosphere and exciting atoms. But along with beauty comes danger. These particles can mess with satellites, damage electronics, and even pose risks to astronauts. Outside the Earth's magnetic protection, like on the Moon or Mars, cosmic rays become a serious health hazard. They can cut through DNA, increase cancer risks, and damage tissues. That's why any mission to deep space has to think very carefully about radiation shielding. Now think about this. Cosmic rays aren't just a modern problem. They've been hitting Earth for billions of years. Some scientists believe that they've actually influenced evolution. By causing random mutations in DNA, cosmic rays may have played a role in how life evolved. Random hits, creating tiny genetic changes, over and over, generation after generation, and during certain cosmic events like nearby supernovae, Earth may have been blasted by waves of extra radiation. There's evidence of this in ancient tree rings and ocean sediments, where scientists have found traces of isotopes that only form during cosmic ray bombardments. One particularly eerie idea: if a supernova went off close enough, it could increase the cosmic ray flux so much that it damages the ozone layer, heats the atmosphere, or even causes mass extinctions. We don't think that's happening now, but it may have happened in Earth's past. And guess what direction those supernovae would be in? You guessed it, above. Which brings us back to the sky. Right now, above your head, the sun's magnetic field is slowly spinning. The heliosphere is shifting. The Earth is orbiting, rotating, and leaning. And through all of it, these high-speed messengers from the galaxy are pouring in, falling from the sky, unseen. They are ancient, they are powerful, and they are relentless. Some are from stars that died before Earth was born. Some might be from things we don't even understand yet. Dark matter, primordial black holes, leftover chaos from the early universe. Some could be warning signs of something bigger, something heading our way in the distant future. But one thing is clear: the space above us isn't quiet. It's alive with motion, radiation, and mystery. And the more we look into the galactic north, the more we realize how little we know. The North Galactic Spur, one of the weirdest things sitting above our heads in the night sky, isn't a planet, a star, or even a black hole. It's something far stranger, far bigger, and far more mysterious. A twisted arc of gas and dust that rises above the plane of the Milky Way and bends back down like some kind of cosmic bridge. It's called the North Galactic Spur. And here's the truth: we're still not totally sure what it is. From Earth, it doesn't look like much, at least not in visible light. If you go out at night and stare upward, you probably won't see it at all. It doesn't shine like Orion or glow like the Andromeda galaxy. It hides in plain sight. But switch on a radio telescope or look at the sky in X-rays, and suddenly, there it is. This giant curving structure stretches thousands of light years above the galactic plane, like a crack across the galaxy's skin. It first showed up in the 1960s, when scientists were mapping the sky using radio waves. They were trying to understand the larger structure of the Milky Way, and they kept picking up this massive arc that didn't match anything else. At first, they thought it might just be a local puff of gas or dust, something close by, maybe even something small. But the more they studied it, the bigger and stranger it seemed to become. Now here's where things get tricky. No one agrees on exactly what the North Galactic Spur is, or how far away it actually is. Some models suggest it could be only a few hundred light years from Earth, placing it right inside the local bubble, a region of hot, low-density gas created by ancient supernovas. In that case, it could be part of a nearby shell, a sort of bubble wall formed by exploded stars that went off relatively recently in cosmic terms. But other researchers think it's much farther away, like thousands of light years. In that version of the story, the spur could be tied to one of the galaxy's major structures, maybe even connected to the Fermi bubbles, those two enormous gamma-ray lobes rising from the galactic center. If that's true, the spur isn't a local flare-up. It's part of something huge, a wound, a scar, a leftover trace of extreme violence from millions of years ago. And what's wild is that both theories might be right. There's growing evidence that what we call the North Galactic Spur might actually be multiple structures overlapping, a kind of cosmic optical illusion. Imagine looking through layers of fog and smoke, with different clouds sitting at different distances, all jumbled together in the same direction. Some of the gas could be close, some could be far, and from Earth, we see it all blended into one long, curved filament. Whatever it is, it's not quiet. The spur is active across multiple wavelengths. It lights up in radio, microwave, and X-ray bands. That tells us the gas inside it isn't just cold dust. It's energized. It's interacting with magnetic fields. It's emitting polarized light. It's charged up, twisted, and dynamic. And that makes it a problem. You see, when we try to measure things like the cosmic microwave background, the leftover glow from the Big Bang, we need to find clean patches of sky, places where there's no foreground noise from our own galaxy, places where we can look past the Milky Way structure and into the early universe. But the North Galactic Spur sits in the way. It contaminates the data. It adds strange patterns, distortions, and false signals that scientists have to carefully subtract or filter out. Some of the early dark matter signals, turns out they weren't from dark matter. They were from the spur. So understanding this arc isn't just about curiosity, it's about clearing the view so we can properly read the sky. Then there's the magnetic weirdness. One of the most fascinating things about the spur is how it interacts with magnetic fields. The dust grains inside the spur are aligned with the galactic magnetic field, meaning they spin and vibrate in a very specific way. That causes them to emit polarized light, a signal that's strong enough to affect instruments like Planck, WMAP, and even the upcoming CMB-S4 telescopes. When astronomers map the polarization of the sky, the spur shows up as a bright, twisting band. And that brightness? It's not because of stars. It's because of how the dust and gas inside it are dancing with magnetic fields. It gives us a rare look at how these invisible forces behave on a galactic scale, which is incredibly hard to study in any other way. Some models suggest the spur could be a magnetized filament, a tube of gas and dust, stretched by shock waves and twisted by magnetic pressure. Others say it's a boundary line between different regions of the galaxy, a kind of interstellar fault line, where two huge zones of space rub against each other. And yet, with all the data we've collected, it still doesn't fit neatly into our maps. Its curve doesn't match standard galactic rotation. Its glow doesn't fade the way we'd expect. Its magnetic alignment is just odd. It's like finding a scar on someone's skin, but no record of the injury. So maybe that's what it is. A scar. A leftover mark from a time when something massive tore through the galaxy. A black hole flare-up, a wave of supernovas, or a collision with a passing dwarf galaxy. Something so violent it sent ripples through the interstellar medium and left behind this twisted, glowing reminder. Or maybe it's something quieter. Maybe it's the edge of a bubble formed by nearby dying stars. Maybe it's local, and we're just seeing it from a weird angle. Maybe we're inside the event, and the arc is the wall. Whatever the truth is, the spur doesn't care. It keeps glowing, keeps bending, keeps sending its signals across the sky. Future missions like Sphere X and Gaia might finally pin down its distance. They might untangle the layers and tell us what's local and what's galactic, or they might just uncover more questions. But until then, the North Galactic Spur stays where it is, high above the solar system, a silent curve in the sky, a structure with no clear beginning, no clear end, and no easy explanation. Not quite a cloud, not quite a bridge, not quite understood, just there, watching. The local bubble. Our solar system isn't just drifting through space. It's floating inside something huge, invisible, and weirdly shaped. It's called the local bubble. And no, that's not a metaphor or some poetic idea. It's real. Imagine a cosmic hole punched out of the galaxy, hundreds of light years wide, not empty, but filled with superheated gas. So thin and spread out it's practically a vacuum, but still carrying the memory of violent explosions that happened millions of years ago. That's what we're in. Astronomers believe this bubble was carved out by a series of supernovae, massive stars dying in massive ways. One after another, they went off like depth charges in the galaxy's sea of gas and dust. Each explosion sent shock waves rippling through space, pushing material outward, heating everything it touched, and blowing away whatever was in the way. Over time, this left behind a cavity, roughly 300 light-years across in all directions, a carved-out sphere in the interstellar medium. And right now, our sun is not just inside that cavity, it's near the edge of it. But the shape, it's not smooth, it's not a perfect sphere. The northern edge of the local bubble, the part above the solar system, is thinner. We know this thanks to data from telescopes and spacecraft like Voyager, Rosat, XMM Newton, and more. They've helped build 3D maps of this bubble, and what they show is pretty strange. The walls aren't evenly spaced. They bulge, dent, and overlap with other bubbles. Because the local bubble isn't alone, it bumps into other cavities, remnants of other stellar explosions. In fact, just above the sun, astronomers suspect there's another ancient bubble, known as the Loop Wine superbubble, that's been pressing down into ours. That pressure, where two bubbles collide, might be warping our heliosphere, squeezing our solar system from above. It could even be changing the direction of incoming interstellar particles and shaping how radiation leaks in from beyond the bubble. Now here's where it gets really interesting. The sun hasn't always been inside the local bubble. It's only been here for the last few million years. Before that, it was moving through a denser part of the galaxy, and now it might be heading out toward new interstellar territory. That transition is what has scientists excited and a little nervous. As the solar system moves, we're heading towards something called the Local Interstellar Cloud, or LIC for short. It's a nearby clump of gas and dust just outside the bubble, and some signs suggest we're entering its edge right now. This cloud isn't nearly as violent as the bubble's creators, but it's denser. Its particles are cooler, its magnetic fields are tangled, and its pressure might be enough to shrink our heliosphere, the protective bubble created by the sun's solar wind. A smaller heliosphere means more exposure to galactic cosmic rays. That's a big deal, not just for astronauts and spacecraft, but potentially even for Earth's climate and atmosphere. Cosmic rays can affect cloud formation, ozone chemistry, and electronic systems on satellites. And what's above us, the northern wall of this bubble, is the first part we're likely to cross. The data shows it's thinner, less shielded, and possibly more turbulent. In a way, it's like flying in a pressurized cabin through a stormy sky, heading toward a region where the pressure drops and the outside air gets rough. You can't see the boundary, but you feel it. This area above the solar system isn't just a transition zone. It's where the heliosphere ends and the galaxy begins. When Voyager 1 passed through this boundary in 2012, it recorded dramatic changes. The solar wind vanished, magnetic fields shifted, and radiation levels spiked. It had left the sun's bubble and entered interstellar space. Not a vacuum, but a place where ancient gas drifts slowly, where magnetic fields stretch across light years, and where the galaxy's real chaos begins. And Voyager did this by exiting northward, above the sun, through the very roof of the local bubble. Now think about that for a second. That means we've already sent a machine through the upper edge of this invisible shell, and what it found confirmed what many scientists suspected. The edge is not just thin, it's dynamic. It bends, stretches, and reshapes itself, depending on pressure from surrounding gas and magnetic forces. It's not a wall, it's more like a fluctuating tide, influenced by invisible weather from other parts of the galaxy. Recent 3D mapping projects have even shown that the local bubble is expanding, not quickly, but gradually. The hot gas inside continues to push outwards, shaping the interstellar medium like breath inflating a balloon. But the expansion won't last forever. As we move through the local interstellar cloud, and possibly into even denser clouds later on, the expansion might stop, and we might see a kind of compression instead, with outside pressure folding the heliosphere inward, possibly altering space travel dynamics and solar protection for good. Even more fascinating, scientists believe the edge of the local bubble may still carry traces of the supernovae that made it. Heavy elements like iron, oxygen, and silicon, launched into space by exploding stars, might still be drifting along its walls. Some of those particles may have even made it to Earth, embedded in Antarctic ice cores or buried in deep ocean sediments. That means our planet carries the fingerprints of ancient stellar deaths, events that happened long before humans ever existed. And those fingerprints, they came from above. This shell around our solar system, invisible as it is, defines more than just a boundary. It's a record of cosmic violence. It's a shield against galactic chaos, and it's a doorway to whatever comes next. Because above us, the local bubble's roof is getting thinner, and beyond it, a new chapter in the solar system's journey through the galaxy is waiting to begin. We just don't know yet if that chapter will be calm or catastrophic. The galactic halo, far above the glowing disk of the Milky Way, past the twinkling stars and the dust clouds that paint our night sky, there's something massive, ancient, and almost completely invisible. It doesn't shine, it doesn't flicker, it doesn't leave trails or echoes like the stars do, and yet, it's there, surrounding everything, holding it all together. Scientists call it the galactic halo, but most people have never heard of it. The galactic halo isn't a ring. It's not a cloud in the way we imagine clouds. It's more like a ghost, huge, faint, and all around us. Picture the Milky Way, that classic flat spiral of stars, about 100,000 light years across. Now imagine a giant, spherical bubble wrapping around it. That's the halo. It stretches hundreds of thousands of light years above and below the galactic plane, like a massive invisible cocoon. We can't see it directly, but we've been able to track its effects. And those effects are huge. Inside this halo are some of the oldest stars in the universe. These stars are different. They don't orbit the galaxy in neat circles like the stars in the disk. Instead, they move in weird, tilted paths, looping far above and below the galactic plane. They're survivors from an earlier time, relics of galaxies that the Milky Way swallowed long ago. Some of them are clustered into ancient globes of stars called globular clusters, which orbit the galaxy like bees circling a hive. They're like fossils, telling the story of how the Milky Way was built, not all at once, but piece by piece, by merging with smaller galaxies. But stars are just the beginning. The halo also contains something else, something we can't see at all, something that, as far as we know, makes up most of the mass of the entire galaxy. That something is dark matter. Dark matter doesn't glow, reflect, or absorb light. It passes right through normal matter, including us. But it has gravity, and it's everywhere. The only reason we know it exists is because of how it pulls on things. Without dark matter, the stars on the edges of the Milky Way would be flying off into space. The galaxy would spin apart like a frisbee made of sand, but instead, it holds together. And the only way that makes sense is if something invisible is holding it in place. That something, dark matter, is thought to form a huge halo around the galaxy. And we're floating inside it. The solar system isn't parked in the middle of this halo. We're off to the side, about 26,000 light years from the center of the Milky Way. And as the galaxy spins, we're carried along with it, slowly orbiting the core. But here's the wild part. While we're moving in a circle around the center, we're also bobbing up and down, like a boat on a wave, through the thickness of the galactic disk and into the halo. Roughly every 30 to 35 million years, the solar system rises above the plane of the galaxy, drifts into the lower parts of the halo, and then sinks back down again. This isn't just some side effect of galactic motion. It could have consequences. Some scientists have even proposed that these vertical oscillations might be linked to mass extinctions on Earth, maybe because the denser regions of the halo disturb the distant Oort cloud and send comets hurtling inward. It's a theory, not a fact, but it shows how closely connected we might be to the invisible forces above us. The galactic halo isn't just dark matter and lonely stars. It's also filled with hot gas, incredibly thin, incredibly spread out, but incredibly hot. This gas, called the circumgalactic medium, is millions of degrees in temperature. We can't see it in visible light, but X-ray telescopes like Chandra and XMM Newton have picked up its glow. It surrounds the galaxy like a fog, faint but vast. Some of the most important clues about this gas come from distant quasars, hyperactive galaxies from far across the universe. When their light passes through the halo of the Milky Way, some of it gets absorbed. That absorption leaves fingerprints, tiny gaps in the spectrum that tell us what kind of gas is out there, how hot it is, and how much of it there might be. And here's something surprising. That halo gas might actually weigh more than all the stars in the galaxy combined. That means we've been underestimating the galaxy's true mass for years. And it also means the halo plays a much bigger role than we thought in recycling gas, forming stars, and shaping the evolution of galaxies. The halo doesn't sit still. It interacts, it flows, it responds. When a star explodes in the disk of the galaxy, the shock waves can shoot upward into the halo, heating the gas and stirring up magnetic fields. When smaller galaxies fall into the Milky Way, they don't just join quietly. They splash into the halo like stones into water, sending ripples through the gas and disturbing the dark matter. Sometimes, streams of stars get pulled out of those small galaxies as they're shredded, creating long trails across the halo. These streams are like scars, evidence of old collisions that are still playing out. One of the strangest structures inside the halo is the Fermi bubbles. giant lobes of gamma-ray energy that stretch 25,000 light-years above and below the galactic center. We don't fully understand them yet. They might be the leftovers from a time when the supermassive black hole at the heart of the galaxy went through an active phase, launching jets of material up into the halo. Or maybe they're the result of a starburst, an intense wave of star formation that blew out massive winds. Either way, these bubbles show that the halo isn't some passive background. It's dynamic, violent, alive, and we're in it, right now. The solar system is passing through the lower edges of this ghostly structure. Every move we make through space is shaped, ever so slightly, by the pull of the dark matter that surrounds us. Every measurement we take of stars, galaxies, and cosmic expansion has to be corrected for the motion we're making through the halo. It's not something out there, it's something we're inside of, always have been. The more we study the galactic halo, the more we realize how little we really know. We can't map it directly, we can't hold it in our hands, but it holds us, and the clues it offers, through gas, motion, and gravity, are leading us towards some of the biggest questions in all of science. What is dark matter really? How do galaxies form and evolve over billions of years? And how does something invisible shape the entire structure of the cosmos? Above the solar system, the halo stretches on, quiet, cold, and hidden, a gravitational giant, softly sculpting the motion of stars. And every time we look up into the night sky, we're not just seeing stars in front of us. We're staring through the edge of a massive mystery we still haven't solved. The Fermi bubbles, galactic shockwaves. Back in 2010, something massive was found hiding in plain sight. NASA's Fermi Gamma Ray Space Telescope was scanning the sky, just doing its job, when it spotted something no one expected. Not a star, not a galaxy, not even a black hole. What it saw was way bigger. Two gigantic lobes of high-energy radiation, one ballooning above the Milky Way, the other stretching below it. Perfectly symmetrical, perfectly sharp, and completely invisible to our eyes. They named them the Fermi bubbles, and once you hear what they are, what they might be, you start to realize how little we actually know about the space we live in. These bubbles aren't small. Each one is about 25,000 light-years tall. That's roughly the same distance we are from the center of the galaxy. So if you could line one up horizontally, it would reach us from the very core of the Milky Way. But instead, they rise vertically, straight up and straight down from the galactic center, like two ghostly towers floating in the halo of the galaxy. But here's the weird part. We don't know exactly what caused them. There are theories, of course. The leading one, that our galaxy's central black hole, Sagittarius, a star, erupted in the past. Maybe not just once, but multiple times. We're talking millions of years ago, maybe more. Back then, it might not have been the quiet, sluggish thing it is today. It could have been hungry, active, explosive. Black holes don't just eat, they also spit. When enough material builds up around them, it can get heated, compressed, and thrown out at near-light speeds in the form of jets. These jets shoot perpendicular to the galactic plane, upward and downward, right where the bubbles are now. If Sagittarius A had one of those violent episodes, it might have launched particles, gas, and radiation out into the galaxy's halo, inflating these enormous lobes like balloons over time. Another theory? A starburst event. A brief, wild period where stars were forming at a rapid rate near the galactic center. When stars are born fast, they also die fast. Multiple supernova explosions could have worked together, pushing gas and particles outwards, driving shocks through the interstellar medium, and carving out these bubble shapes. But whatever the cause was, it left behind something huge and hot. The Fermi bubbles are filled with high-energy particles, mostly electrons moving at close to the speed of light. These particles are slamming into photons, converting them into gamma rays, the most energetic form of light in the universe. That's how the Fermi telescope spotted them. They're also surrounded by sharp edges, which is even stranger. You'd expect soft, blurry boundaries if these bubbles were just slow gas clouds. But their borders are well defined, like someone cut them out with a knife. That tells us they're probably not drifting lazily. They were created by something fast, violent, and focused, and they're still here, even millions of years after the explosion, or whatever caused them. They're still glowing, still expanding maybe, still doing things we don't fully understand. Some scientists think the bubbles are still interacting with the material around them. As they push outward, they collide with the hot gas in the galactic halo, creating shock fronts, waves of compressed gas and magnetic fields. Instruments have picked up X-rays and radio waves from these areas too, showing that the bubbles aren't just gamma-ray zones. They're multi-layered, multi-wavelength, and multi-mysterious. And here's a visual for you. If human eyes could detect gamma rays, you wouldn't see stars in the night sky. You wouldn't see constellations or planets. You'd see these enormous pillars of energy, stretching above and below the galaxy. The sky would look like it's being pierced by two glowing beams from the heart of the Milky Way, like giant cosmic lungs exhaling light. But because gamma rays are invisible to us, the sky looks quiet, peaceful, safe. It's not. Gamma rays don't just hang out. They come from the most extreme environments in the universe: supernovae, neutron stars, black hole jets, and violent particle collisions. The fact that these bubbles are so rich in gamma radiation tells us they were born in chaos. There's more. The Fermi bubbles aren't the only strange thing up there. In the same region, especially above the galactic center, there's another feature called the North Galactic Spur. It's a huge arc of gas, dust, and magnetic activity. Some maps show that the bubbles in the spur might overlap, or at least interact. That means the Fermi bubbles aren't just floating alone. They're part of a bigger, more complex structure that we're still trying to untangle. Then there's the microwave haze, a fuzzy glow that sits in the same area. Some think it's leftover energy from the same event that created the bubbles. Others think it might be something entirely different, maybe even a signal of dark matter interactions happening nearby. That's the thing with the Fermi bubbles. Every time we learn something new about them, it just raises more questions. Are they still growing? Are they fading? Will they collapse? Are they evidence of something our galaxy used to be, a more dangerous place with a more active core? And if that happened once, could it happen again? That's not just science fiction. Some researchers believe we're overdue for another burst from Sagittarius A star. It might not be strong enough to hurt us, but it could light up the galaxy again, create new bubbles, or expand the ones we've already found. Right now, missions like Erosita and X-RISM are scanning the skies in X-rays, trying to map these bubbles more precisely. And future telescopes, especially ones tuned to gamma rays and high-energy particles, could finally help us figure out what exactly we're looking at. Until then, the Fermi bubbles sit above us, silent, massive, glowing with energy that could melt a star. A reminder that our galaxy isn't just a pretty spiral. It has a memory, a temper, and scars. We don't see them in the night sky, but they're there, watching, waiting, and whispering stories from the heart of the Milky Way. Dark matter filaments, above us, wrapped in silence and stretched across space, might be something that shapes the very structure of the universe, without giving off even a hint of light. Something massive, something invisible, something we know is there, because of everything around it. Dark matter filaments. They're not science fiction. They're not just theories either. In the last few decades, astronomers have come to believe that our entire universe might be laced with long, thread-like structures, cosmic rivers of gravity, woven between galaxies, like an enormous spider web made of shadows. These filaments don't shine, don't reflect, and can't be touched, but they seem to be the scaffolding on which the visible universe is built. The idea comes from simulations. Supercomputers running models of how the universe evolved after the Big Bang keep showing the same pattern over and over, a vast network of filaments forming as gravity pulls matter together in strange, web-like shapes. At the junctions, where these filaments intersect, galaxies gather like dewdrops on threads, and in between them, empty voids, massive spaces where there's almost nothing. The wild part is, our Milky Way isn't outside of this web, it's inside it. And some scientists believe that the solar system might be moving right through one of these filaments right now, passing through a section of dark matter that stretches above and below the galactic plane. If that's true, then our little patch of space is surrounded by something we can't detect directly, but that still affects everything around us. Dark matter itself is one of the biggest mysteries in all of physics. We can't see it with any telescope. It doesn't absorb light or emit it, but we can measure its gravity. We know it exists because stars on the edges of galaxies move way faster than they should. They're whipping around like they're being tugged by something massive, but we can't see what it is. The only explanation that makes the math work is that something invisible is holding galaxies together. That something is what we call dark matter. Now imagine that dark matter not as a shapeless cloud, but as something structured, formed into long filaments. These filaments stretch for hundreds of millions of light years, creating bridges between galaxy clusters. They're so vast and so quiet that entire civilizations could live and die without ever noticing them. But these filaments leave a trail. When light from distant galaxies passes near them, it bends. That bending, called gravitational lensing, is one of the ways we've mapped out where dark matter might be hiding, and it gets crazier. Some astronomers think smaller dark matter strands, tiny compared to galactic filaments but still enormous by human standards, might exist within galaxies too. Inside halos of dark matter like the one surrounding the Milky Way, there could be little streams or tendrils of denser material. If one of those is drifting across our path, it could influence how nearby stars move. It could subtly pull on our solar system. It could even be warping the orbits of comets, or causing mysterious gravitational effects we haven't yet understood. There's even speculation that Earth has already passed through one of these dark threads in the past, or will in the future. We might not feel anything directly, but a sudden shift in gravitational balance could disturb the Oort cloud, that distant shell of icy bodies that surrounds our solar system. And when the Oort cloud is shaken, comets start falling inward. Some researchers have even wondered if dark matter filaments could be loosely tied to cycles of mass extinctions on Earth. It's still a fringe idea, but it shows just how strange and powerful this invisible stuff might be. It's humbling to think that there might be rivers of mass flowing silently above our heads, not made of gas or stars or planets, but of something we barely understand, something that only makes itself known through the way it tugs on the things we can see. Our best tools, gravitational lensing, sky surveys, simulations, and high-precision star mapping are finally starting to give us a glimpse of this hidden architecture. Projects like ESA's Gaia mission are tracking the motion of over 1 billion stars in our galaxy. And from that data, scientists can look for tiny anomalies, drifts, curves, and shifts that hint at unseen gravitational influences. Some of those could be dark matter clumps or filaments crossing the galactic plane. What's beautiful and eerie is that even though these structures are invisible, they're not random. They're ancient, precise, and deeply organized. The galaxies follow them. The stars follow them. We follow them. Above the solar system, there might be one of these ghostly threads stretching quietly across the void. We can't see it, but it's there, holding us in its grip, guiding us through the galaxy, and waiting for the day we finally understand what it is. Rogue planets. Some planets don't have a home. They weren't born under a steady sun or locked into cozy orbits like Earth. They were kicked out, flung from their systems like cosmic orphans. No sunlight, no host star, just endless night. These are rogue planets, and they're real. For a long time, astronomers didn't know if they even existed. The idea of a planet without a star seemed weird, even impossible. After all, how do you even form a planet if there's no star for it to orbit? But as our telescopes got better and our models more detailed, the evidence started to build. Not only are rogue planets possible, they might be everywhere. Some of them are born in violent systems where gravity throws a tantrum. Picture a young star surrounded by dozens of planets, all jostling for position. If two planets get too close, one might get slingshotted out, ejected into interstellar space. Forever. Others may have formed in gas clouds that never became stars. Just clumps of material in the void, growing large enough to become planets, but never lighting up. Once they're out, they drift. No orbit, no direction, just a slow, cold fall through the galaxy. Now here's where things get interesting. Some of these wanderers don't stay far away. They pass near other systems, and some pass near ours. If a rogue planet were to approach the solar system, you probably wouldn't see it coming. They're pitch black, no glow, no reflection, barely even visible to infrared sensors unless they're close. And because most of our space surveillance is aimed along the solar system's plane, we're not watching everything above us. That's a blind spot. And that's exactly where some of these objects could be falling from. When astronomers say above, they're talking galactic direction. Our solar system lies in a flat disk, like a dinner plate. Above that plate, into the galactic north, is mostly unexplored territory. And rogue planets don't care about neat orbits or planes. They can come from any direction, including straight down. So what happens if one gets close? Well, it depends. If it sails past, we might barely notice, unless it messes with the Oort cloud, a giant swarm of icy bodies that surrounds the solar system like a shell. A rogue planet's gravity could shake loose thousands of comets, sending them tumbling inward over time. Some might never make it past the outer planets, others could light up the sky, and a few, on rare occasions, could come a little too close to Earth. Worse, if the rogue planet came in closer, let's say it moved through the Kuiper Belt or near Neptune's orbit, its gravity could tug on planets, tilt orbits, stretch asteroid paths. It wouldn't have to crash into anything to cause chaos. Just a gentle nudge from something 5 or 10 times the mass of Earth could ripple through the whole system. That's not science fiction. It's physics. There's even a theory that our mysterious, hypothetical Planet 9, the one some astronomers think is hiding in the far reaches of our solar system, might be a captured rogue planet. Something that drifted too close and got snatched up by the sun's gravity, locked into a distant, lopsided orbit. We still don't know if that's true, but if it is, it wouldn't be the first time the galaxy sent us a visitor. Microlensing has helped confirm that rogue planets exist. That's when a planet passes in front of a star from our point of view, and its gravity bends the star's light like a lens. For a brief moment, the star seems to brighten. And in that moment, we can tell there's something dark out there, blocking and warping the light. Using this method, scientists have found rogue planets as small as Earth and as big as Jupiter. And not just a few, possibly billions of them in the Milky Way alone. Think about that. For every star we see, there could be more planets not orbiting anything at all, and we're not tracking most of them because they're silent. They don't shine, they just move, slow, quiet, and cold. So when we ask what lies above our solar system, the answer might be unsettling. Stray worlds, lonely giants, invisible travelers falling toward us from the galactic north. They've been drifting for millions of years. No destination, no light, just momentum and gravity. And maybe one day, one of them gets close enough for us to finally notice. Let's just hope it stays in the dark. So here's the truth. We've been staring sideways at space, obsessed with what's out there, forgetting to look up and down. But above us, that's where the heliosphere thins, where rogue planets drift, where ancient light enters. That's where the universe opens into clarity. And below us, another pole, another perspective, another whole half of the unknown. The solar system is not a flat playground. It's a bubble in motion, rising, spinning, dodging invisible winds and ancient scars. We're passengers in a vertical journey we barely understand. And the scariest part? The most powerful forces, gamma rays, dark matter, gravitational pulls, they're not coming from in front of us. They're falling from the sky. Next time you look up, remember, you're not just seeing stars. You're staring into the most mysterious part of the galaxy. What lies above and below us might not just shape the solar system. It might define how the universe works. There's a cosmic highway above our heads, filled with shadows, particles, planets, and power. And we're just beginning to read the signs.